Okay, so just like with a linear system, we had two methods, really three methods for solving a system. We have that additional method here when we're looking at nonlinear systems. So we're going to solve these systems using the addition method. In this first example, we have y squared minus x is equal to 4 and x squared plus y squared equals 4. Just to kind of give you an idea of what we're looking at here, this is a sideways parabola and this is a circle. So we have two definite nonlinear equations that we want to solve for. The idea though is if I'm using the addition method, I want to be able to add like terms together to get 0. So I have a y squared and an x squared and a y squared. So these two y squareds are the only candidates for me to be able to add together to get 0. So let's rearrange the equations, lining the like terms up. So I have y squared minus x is equal to 4, and here I have y squared plus x squared equals 4. Y squared and y squared are like terms. If I want to add those two coefficients together to get 0, then they actually are close, but they need to be opposite in sign. So I'm going to just take the first equation and I'm going to multiply by a -1. So I'm going to change every sign in here to the opposite. That's going to allow me to add these two numbers together to get rid of the y squareds. So when I do that, I get x squared. I can't combine that with an x, so I just get x squared plus x equals 0. Now I want to take a second and tell you why I chose the first equation to make negatives. I did that for a reason, because when I added them together, I knew I was going to be eliminating the y's, but if I had chosen to multiply this equation by a negative, it would have left my leading term, the largest power, as negative. In other words, x squared would have been negative this time. And I don't like my leading variable or my leading coefficient to be negative, so I chose to make this term I chose to multiply the first equation by a -1. Okay, so here I am, and now I'm going to solve for the variable x. I do that because this is set equal to 0 by factoring the left-hand side into x times x plus 1, and then setting each of these factors equal to 0 and solving. So x is equal to 0 and x is equal to -1. We take what we know now x to be, and we're going to substitute that back into the first equation here. So I'm going to substitute it into this equation and solve for y. And I'm going to do it to this one because, I don't know, because I didn't want to have to square my variable. So I'm just going to take an easy road and do it in this one. So y squared minus x equals 4 is the variable that I'm going to substitute x into each time. So this is y squared minus 0 equals 4. Y squared would be equal to 4, and when I take the square root of both sides, I find out that y is equal to plus or minus 2. Remember, if I take the square root of a number, I get a positive and a negative value. That says when x is equal to 0, y is equal to a positive 2, and when x is equal to 0, y is equal to a -2. So I have two solutions for this portion, and we're going to go back in and we're going to try this again. Y squared minus x equals 4, but this time I'm going to let x be equal to -1. So y squared minus a -1 equals 4, or y squared plus 1 equals 4. So if I subtract 1 to the right, I get y squared is equal to 3. And yes, I can take the square root of both sides. It just doesn't give me a perfect answer. I find out that y is equal to plus or minus the square root of 3. So when x is equal to a -1, y is a positive square root of 3. And when x is equal to a -1, y is equal to a negative square root of 3. And those four solutions are the answers to this system of equation. And let me just kind of give you a description of what this is. I told you at the beginning that this was a sideways hyperbola and a circle. And so we have these four places that the two functions are intersecting at, and that's what's represented right here. So picture maybe the orbit of a satellite, I don't know, something like that. You don't want your satellites to crash into each other, and so we have these ideas where if we are, if I have something I'm sending up into space and I guess I'm never getting it back if it's this parabola, and I have another orbit here of something else hovering around space, I don't want these two expensive pieces of equipment to crash into each other, so I have to make sure that they don't intersect with whatever orbit I send them on. Let's try one more time, and let's look at this system of equations here, because this one looks just a little bit different. But it's going to be the same concept when I try to add these two functions together. So I'm looking at these four variables. Now I know that this is not exactly a y squared in the way that it is right now, but eventually it would be if I were to expand this out. But I don't really care about doing that right now because I have enough information by looking at these two x squareds here. These two are exactly the same. They are like terms. So if I were to multiply through by a negative and add them together, it would eliminate the x squareds immediately. And that's what I'm going to choose to do in this system. So I'm going to make this a negative, and a negative. In other words, I multiplied the first equation by a -1, and when I add them together, that x squared plus that x squared is 0, giving me, and I'm going to write it like this, y minus 8 squared, because it's positive, minus y squared equals -5 plus 41, or 36. Now let's go ahead and expand this out. This is square the first, double the product, which is 16y, and square the last, which is 64, minus the y squared we already had, equals 36. So collecting the like terms, the y squareds disappear. I get -16y plus 64 equals 36. I don't know why my dot stayed there. Now I'm going to subtract 64 to the right. -16y is equal to -28. Divide both sides by -16, and I get a 7/4 for the answer. So remember, I told you that fractions exist out there in the real world, so we're going to continue on knowing that y is equal to 7/4. I'm going to go back in and I'm going to substitute into the first equation, the original first equation, because it is kind of the easiest one to substitute into. So if I have x squared plus y squared is equal to 7/4. Oops, not 7/4, is equal to 5, I meant to say. We are going to let y squared, or y, can't write right now, x squared plus 7/4, because that's what y is, squared equals 5. So on my calculator, I am going to square 7/4 and I'm going to subtract it from 5. So if I square 7/4 and I leave it as a fraction, which is what I wanted to do because I think that's easier, if I square 7/4 I get 49/16. So I have x squared plus 49/16, which I could have totally done in my head, and I'm going to now subtract it from 5. So I do that on my calculator as well. So I'm going to say 5 minus the previous answer, and I want the exact answer, so I'm going to go ahead and leave it as a fraction, and I find out that it's 31/16. So x squared is equal to 31/16, and when I take the square root of both sides, I get x is equal to the square root of 30 plus or minus the square root of 31 on the top, and the square root of 16 is just 4. So what do I know? I know that the solutions to this system of equation are going to occur when x is the square root of 31 over 4 and y is 7/4, and negative square root of 31 over 4 and 7/4. So these two functions are actually just intersecting twice. And that's how we come up with the solution for these nonlinear systems of equations by using the addition method.